So how could we think about modeling this in more of a realistic neural circuit type model? So you will remember that we studied this neural circuit model of working memory by Brunel and Wang, in which there were multiple selective populations of excitatory cells, each simulated with leaky integrate and fire type models. And this was capable of producing stimulus selective persistent activity. So to study decision making, we can start to look at exactly the same model, but now we just focus on two competing excitatory populations, for example, that prefer a leftward stimulus and a rightward stimulus. And we still have a non-selective population, and all of these excitatory cells are communicating with inhibitory neurons, also known as interneurons, as before. But now, instead of inputting a transient stimulus to one population, what we're going to do is we're going to input a sustained stimulus to both populations, A and B, and this will represent, for example, the different levels of coherent motion in the left direction versus the right direction in the random dot motion task. Now, if we study this model during the input of two different stimuli, that is a slightly stronger stimulus to population A and population B, which represents partially coherent motion towards the favored direction of population A, what we see is this increase and build-up of firing activity in the population A, and you see very little activity in population B. If we decrease the coherence so that there are more dots moving towards the favored direction of population B, we now see that there's a bit more activity in this rightward population B. And if we put in a even stimulus to both neural populations, that's 0% coherence, what we see is at the beginning of the trial, shown on the left here, there's fairly similar level of activity in both populations, but over time activity ramps up more in one of the populations than in the other, and eventually this seems to win a kind of competition and decrease activity in the other population. So we can see that even when there is completely incoherent motion, this network seems to be able to flip a coin and randomly choose whether to respond to the left or to the right. We see that the buildup of information for the more coherent stimulus ramps up a little bit quicker, shown by this line with this higher slope, compared to the situation in which there is less coherence. So this signal ramps up more slowly towards the decision threshold. So let's look a little bit more in detail at this case in which there are even stimuli or a motion stimulus with zero coherence. Here again we see population A activity shown here in red and population B activity shown here in blue. At the bottom here we see the strength of the stimulus, which is roughly even, but varies a little bit around the even line over time. This is shown for a period of 2 seconds. And what we see here is the average firing rate of the two populations. And it seems to be very even over the first few hundred milliseconds. But after a while, activity of one of the populations starts to build up, and it seems to be maintained close to a high level of persistent activity. Now what we can see here is if we plot activity of population RA on the x-axis and RB on the y-axis, we see that every time in the trial when there's zero coherence, initially activity moves along this line, which represents even level of activity between both populations, but gradually it moves off this center line towards activity dominating in one of the two directions. And we can see multiple different repeats of the simulation with zero coherence here. Sometimes it goes up to A, sometimes it goes down to B, but there's always this initial period in which the network seems to be uncertain before a decision is made. Now this is a network with even level of inputs to both populations, except for noise, which changes from moment to moment, and it also has an even level of excitatory connections in both populations. So the network is in theory symmetric, but due to the strong recurrence and the noise, you're able to break that symmetry and you're able to make a choice even with equal inputs. Now, this is quite a complicated model, so even for this model that we've simplified a little bit, as it only has two populations of excitatory cells that are selective and one non-selective population and one inhibitory population, that's still 2000 neurons, that's 1600 excitatory cells and 400 inhibitory cells. And you'll remember from the working memory lecture that each of the excitatory cells has a few corresponding dynamical variables. There's the firing rate. We also had two dynamical equations for NMDA for each cell and one dynamical equation for AMPA. So for 1600 excitatory neurons, each with four dynamical variables, that's 6400 equations, and the inhibitory neurons have a firing rate and a gating variable for GABA, so that's 2 times 800, so that's 7200 differential equations here and dynamical variables that we need to calculate, and that's quite a lot. So Wang and Wang in 2006 wondered if this model could be understood a little bit more easily by reducing the complexity of the model and moving to a mean field version of the model. They started by realizing that for this system, we're mainly interested in the firing rate of the population, and within each of the selective pools of neurons, the selective populations, all of those neurons are contributing to the same calculation. So we can actually start by plotting, instead of the spiking of each individual neuron, the firing rate of the overall population, that is the mean firing rate across all of the neurons in the population. And this instantly brings us down from 7200 equations to just 11 equations, 11 dynamical variables that we need to calculate. And the way they were able to reduce to 11 was that they realized that the rise term of the NMDA receptor could essentially be accurately calculated as a simple function of the input firing rate times a constant due to its rapid onset time. And one of the ways we can do this is by replacing the input-output function of individual neurons with this simplified input-output function, which is also known as an FI curve. This is based on work by Abbott and Chance. And this is the equation here, where you have input current, which can come from external sources, as well as local recurrent connections in the network. And the firing rate output rises in proportion to a slope, A. There's also a threshold term, above which the current starts to rise above 0. And then there's this other parameter, D, which basically tells us how quickly, how sharply this rises at a low level of current. So here I've shown an example when this D is very high, and what you see is something like a threshold linear function here. However, it's more normal to use a function which looks a bit like this, so it's a little bit non-linear at low levels of input. Okay, so now we've reduced down from 7200 dynamical variables to just 11. And when you simulate this model, it turns out that the activity of the non-specific excitatory cells that don't have a particular preferred direction is not particularly important. In fact, the activity of these cells seems to stay roughly constant over most of the trials and most of the time. So we can effectively remove this population, and this removes 3 further dynamical variables. And now we have just 2 populations of excitatory cells, each selective for opposing directions, and 1 population of inhibitory cells. And these are defined by these equations here. The firing rates of the excitatory populations are updated using essentially a very similar equation, or the same equation as for the inhibitory cells. This phi high here is just this function here. So it takes an input current and converts it into a firing rate here. We also have the dynamical equations that we've seen before for AMPA and for GABA, and this is just a slightly simplified version of the NMDA equation with just one equation describing the NMDA dynamics now. Then we try to simplify the model even further. So first of all, it turns out that in this network, the firing rate of the inhibitory neurons is always quite high, and that means that they're always in this linear part of the FI curve, or the input-output function. That means we can easily remove the dynamical GABA variable and express it as a linear function of the inputs from the other populations. And this reduces further our system by removing this I population. The firing rates of the neurons in the system update very quickly, almost instantaneously. So we can also remove the dynamics of the firing rate variable. And you'll remember from previous lectures that the time constant of NMDA is much longer than the time constant for AMPA. So we can assume that the AMPA dynamical variable reaches its steady state much sooner than NMDA. And therefore, the AMPA dynamics become essentially a constant function of the input firing rate. So over this decision, which takes place typically over hundreds of milliseconds, the only really important dynamics seem to be happening in this slow NMDA receptor. So this allows us to reduce this model, which initially had 70 to 100 differential equations, down to just 2 differential equations. And we're only interested now in the dynamics of the NMDA receptors in the populations that favor direction A versus direction B. And here we see again, just to remind us that the time constant for NMDA is much longer than the time constants for AMPA, GABA, and the firing rates indeed. Now, this reduced model seems to do a very good job at reproducing the monkey behavior. Here we can see the monkey behavior with increasing coherence. It goes from close to chance, when the coherence is very low, up to almost perfect behavior. The spiking network model that we studied a few slides ago reproduces this very well, and the simplified rate model with only 2 equations also does a very good job. Here in the rate model, we can see with high, medium, and low levels of coherence, the integration of the information and the increase in the firing rate towards the threshold. Here we can see the reaction times in the model. If we read out the time at which population activity reaches this threshold, these are the real monkey reaction times in the experiment. In the spiking network model, we see that for correct trials, shown in the black line here, for higher coherence, the reaction times go down in a very similar time scale to the monkey, whereas you don't really see for the incorrect trials, these don't seem to go down very much at all. And then the firing rate model, the very simplified model, we also see quite a similar curve of decreasing reaction time with higher coherence or easier decisions. So this very simple model seems to do quite a good job at reproducing both the ramping activity we saw in area LIP of the monkey cortex, as well as different aspects of the behavior.